Okay, now really, off the top of my head, I can think of three big deal things in this course. One is motion along a path and being able to analyze the motion, find your unit tangent normal, your components of acceleration, get to, tangent and normal to the curve, the inward normal direction, the outward normal direction, osculating circles, and all that stuff. So that's really important. Okay, gradients are really important. Okay, you have things like gradient descent method where you analyze something in any number of dimensions and try to figure out where its minimum is, but you're never sure. But you know if the gradient keeps descending, you're going to get at least a relative minimum. And of course that goes in with maximum and minimum of a function. So that's off the top of my head. That's a big deal. And chapter 16, okay? Everything else is kind of building toward chapter 16. Now, that doesn't mean moment integrals and centers of mass and so forth are unimportant. They are important. And they're kind of secondarily central to the course. You really have to understand them. But you have to understand everything up to this point to understand chapter 16. Okay? There's another type of integral that we haven't talked about. It's a surface integral. That comes next week. We'll talk about that, and I love to talk about it. But what really is central to understanding things like hydrodynamics and electromagnetic fields and so forth, and a lot of stuff that I don't understand very well, not that I claim to understand anything very well, is flux and circulation. And that's really the capstone of this course that involves flux and circulation. So we've really got to understand those things. So I want to talk a little bit about flux and circulation. Okay, flux.
I think if that's just the title, up top, you don't need to move the camera or anything, but I can't see.
That's just the title, but let's move the camera. You deserve to be able to see it. Okay, flux and circulation. And I should have checked the camera. I've really got it right there, which is why I keep looking over here. Flux and circulation. Okay, flux. I'm going to draw a picture. Now, we haven't drawn pictures of vector fields, but you're doing that in section 1, and you'll pretty much understand. So if you don't understand what I'm saying here, come back to it after you've done section 1 of chapter 16. And you might run into some problems in section 1. That's why you got to let me know if you need to meet on Thursday. Okay, flux and circulation. Okay, so here's curve. And for some reason, okay, you've got some kind of, the easiest thing to understand is probably a fluid flowing. You can also understand this as an electromagnetic field, a force field, a stress field, whatever. Okay? But you've got some field here. Maybe the field looks like this here, and by the time you get here, maybe it's this way, and this way, and so forth. Okay? The flux is the integral of the normal component of the field, normal to the curve. Okay, so flux and we often use the Greek letter phi for flux. Of course, we also use the Greek letter phi for potential functions a lot of times, so you got to know the context. And if the potential function and the flux are both important, which is very often true, you probably want a different notation for the flux, but I'm going to call it phi. Intuitively, the flux phi is the amount of fluid that flows across this surface. So if this is these are velocity vectors for the flow of a fluid. Let's say you got a thin creek, of very small depth and not a real fast flow, so the flow is pretty much constant from the top to the bottom, although that's not really true. This will tell you how much water, let's say, is flowing across this imaginary curve. So measure the flow of the creek. Now, why you'd have a curve of this shape and measuring the flow of a creek, well, it could depend on obstacles in the creek and so forth. You might want to have something that looks like this, but more likely just have a straight line from one side of the creek to the other. Anyhow, the flux is the flow across C. So here's your curve, C, and here's your field, f of x, y. Now none of this depends on the field being conservative. Okay. But anyhow, the flux is the flow across the curve. Now what do we mean by the flow across the curve? Well, let's take a small segment of the curve. And you know that you could, if you could parameterize this curve, and it's a parameter t, for example, you could then partition the t interval and get little segments of the curve. So let's just say we've done this. And to understand the flux, in a typical subinterval delta Ti, where I'm using kind of an ambiguous notation for this, but you should understand from context. Okay, if the flux across a subinterval delta Ti is, well, let's draw a picture of it. Okay, so here's your delta Ti. And it goes from x of ti minus 1 to y of ti minus 1 to x of ti, y of ti. And you've got your sample point, which I'll just label x star y star, and whatever your x function is, this means the x function evaluated at ti star, which is the sample point within this interval, and I'm going to regard that as implicit because I don't have time to write it all out. We've got 11 minutes to go here, you know. Okay, so right there's your x star y star, and you have your function, your vector function f evaluated at x star y star, which means x evaluated at your parameter t at the sample point. Okay, well, you have then a normal vector, and let's make it a unit normal vector. And is your unit normal? Well then, can we have a delta S C? Delta S is determined by your parameter space at the sample point. So I'm not going to do an arrow that, but interval length is this. The amount of fluid that flows, the rate at which fluid flows across this surface is going to be the component of F perpendicular to the surface. Because a flow parallel to the surface isn't going to flow across the surface. Only the part of the flow perpendicular to the surface flows across. Now I could go on about that a little more, and it'd be nice if I could, but for time I'm going to just leave it at that and state. It's going to be F perpendicular times delta SI star, where F perpendicular is the value of X star, Y star, and X star is X of TI star, and so forth. Okay? The picture is if here's your normal, it's a unit normal. And here's your F at X star, Y star. You know that we could have vectors F parallel and F perpendicular. So we have didn't leave myself a lot of room, did I? F perpendicular here, and F parallel here. Okay? So F perpendicular gives you the flow through the surface per unit length of the curve, because F parallel is, as obvious, parallel to the surface, or the curve. Now you do this in 3 dimensions and have a flux over a region, a 2-dimensional region, but you have to do surface integrals to do that, and we haven't yet. But there's a simple analogy. Okay, F parallel is parallel to the curve. And let me check my time. Yeah, okay. Thought I'd restarted. And yeah, we're recording. F perpendicular gives a flow through the surface because this is parallel to the curve. So it never passes through the curve, and you can visualize that. It's an intuitive idea that we don't have time to get into a deeper proof of. And it then follows that flux delta phi I star is and I could even put a star on the F as evaluated at the sample point with, you know, F is evaluated at X, Y, X is evaluated at TI, and so is Y. Now what is F perpendicular? Well, F perpendicular, as we know from our analysis back a couple chapters earlier, when we analyze motion and so forth, is just F dot n, and n is also evaluated at your sample point. So dot 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 so phi is the integral over your curve of f dot n ds, where ds is a vector, and I probably should have made that a vector in some previous integrals, but maybe not, because I think we were just doing scalars then. Okay, so there's your phi, there's your total flux. Now you set this up as a sum, then you do the magic and approach the integral, and you want to understand the magic. But that's it. Okay, that's flux. Now, the details, of course, you got to be able to find your normal vector, but you know how to do that. You might have to review it a little bit and reinforce it, but that's good for your soul. Okay, so there we have it. Now, circulation. Is usually done in reference to a closed curve, but just with respect to this curve, the circulation is just the integral of the component that's parallel. If we understand this picture, we understand that the parallel component is circulating along this curve, so that if we had a field here, maybe it looks like this, you can see that the components of this field parallel to the curve maybe look something like this. Just projecting all the force vectors, all the circulation vectors, all the flow vectors onto the direction as indicated by the unit tangent. These blue arrows show that you have a tendency to circulate around this curve. Okay, so that's why we call this circulation. And if you do this, you can do this, because all this requires is that you have an expression for your unit tangent vector. Now, we have less than a minute to go. That's well timed, because that's about all I had to say. We build on this, and your big integrals, Stokes' theorem and divergence theorem, invoke circulation and flux.